Okay, welcome back. Today will be the last of the examples that we're going to do on optimization before we move forward to the next topic. So I just wanted to do two more examples. One of the examples will again be a rectangle problem, but it will be slightly different from what we saw before. Let's suppose a farmer has a fixed amount of fencing, and they want to enclose a rectangular area, so you still have a rectangle, but they want to divide it into 4 pens with parallel sides. 2, 3. So what's the largest possible area they could do? So in this case, the way we have it set up, you have the entire, you have this big rectangle that's been changed into these smaller rectangles. 1, 2, 3, 4 of them. Okay, and then so if we call each of them having a little width W and a length L, we could find what the largest possible area now. So all these lengths, and actually, just for ease of notation, instead of calling them all W's, I'm going to call the total length of this side, I'll call that W. Okay, so our area is still length times width, right? If you look at the big rectangle, the length of the big rectangle is still the length of all these smaller ones, right? Because they're all parallel sides. And the width of the entire big thing is going to be the width of the big rectangle. Now, what's the perimeter? Well, first of all, we know we have 750 feet of fencing to work with. That's about the perimeter. But to do the perimeter, we need to count what the sides we have. Well, we have 1 and 2 of the W's, and then we have 1, 2, 3, 4, 5 of the L's. So the formula is already looking a little different than it did last time. So we can solve for one of them, like say W. So 2W equals 750 minus 5L, or W equals 375 minus 5/2 L. And that's just dividing both sides by 2. Okay, so then what do we do with that? Well, you have the area equals length times the width is 375 minus 5/2 L. And you distribute it. 375L minus 5/2 L squared is what our area is. Now we want to maximize it, largest possible area. So first derivative test says we want to find the first derivative, which is 375 minus 5L using power rule. We want to find its critical numbers. Well, that's defined everywhere, so we solve that equal to 0. What do we get? We get L equals, well, you add 5L over, equals 375, so L is what? 75. Okay, so we still have to check, is that our maximum value? So you have 75, you could plug in, let's say, 1 is less than 75 and 100 is greater than. If you plug in 1 into the derivative, you'll get 375 minus 5 is positive. If you plug in 100, you'll get 375 minus 500 is negative. So we do have this maximum. And the endpoints of having something like L equals 0 does not make any sense. Because in that case, you do not have a rectangle anymore. So it looks like L equals 75 is what the length that will give us the largest possible area. But this problem asks, what is that possible area? So we need to go back to this formula and plug in L equals 75, and we'll get what that area is. So the area is 375 times 75 minus 5 halves, 75 quantity squared, which is going to be 14,062.5. And that would be square feet. So that's one example. Now let's move on to another one that is going to be geometric in nature. So find the dimensions of the largest rectangle that can be inscribed in a circle of radius r. So remember, you may or may not remember, but the idea behind inscribing a rectangle is I have a rectangle and I have a circle such that if you look at this point right here, the corner, that is touching the outside of the circle. That is the distance from the center of the rectangle to the corner is the same as the radius of the circle. I'm sort of making sure that this rectangle is lying inside the circle. Okay, so if we do that, we want to find what's the largest rectangle that we can do that with, where our circle is radius r. So we know the area of a circle, well, that's pi r squared. And we know what the area of the rectangle is, that's length times width. Okay, so what's the length? Well, if I put this on a coordinate plane, and this is my y value, is that point right there. This is a y, x comma y. Then my length will be 2 times the y. Right, because you have this vertical distance and this vertical distance. And there's still the radius going to this corner, so that's the same. It's just a negative y, x comma negative y. So our length is 2 times y. What about our width? Well, the same thing goes. You have this length and this one. So our width is 2 times x. Okay, so how can we get so just drawing it again down here, how could we solve for one of these? Because now, what do we have? We have area equals 2y times 2x, and we have 2 variables. Well, here's our r, and you have x down here, and you have y. Well, remember, we could use Pythagorean theorem. They're going to be perpendicular to get that our x squared plus y squared equals r squared. Or, let's say y equals, well, it's a distance, so we'll take it to be positive, r squared minus x squared. Okay, so let's plug that into this area. There's 2x and 2y, so that's a 4. And there's an x, square root, r squared minus x squared. So now we have a formula. This r value it's a fixed radius. I didn't tell you what the radius was, but it's just a number. And then x is our variable, our independent variable, and we're looking to find the largest area. So we need to maximize this thing. Let's take the first derivative. This is the product rule. So the derivative of the first times the second plus the first times the derivative of the second, and through chain rule, that's 1 over 1/2 r squared minus x squared times negative 2x, and that was just with chain rule. Simplify this a little bit. You get minus, and then you have a 4x squared over square root r squared minus x squared, because these twos cancel. Okay, so where is that equal to 0 or undefined? Well, it's undefined if our x is greater than r, which will not happen because that will geometrically not make any sense, or if x is equal to r. But if x is equal to r, our y is 0, so that's not going to be a circle, which means in our domain this is defined, so we set this equal to 0 and solve. So 4 square root r squared minus x squared equals 4x squared over square root r squared minus x squared. Multiply the square root to both sides. You get this, that 4 quantity r squared minus x squared equals 4x squared, because it cancels this one. And with this one, you have a square root r squared minus x squared times a square root r squared minus x squared. So that gives, instead of to the 1/2 power, to the first power. Okay, so let's solve this. For r squared, well, before we do that, you could divide by 4. Both sides, you get r squared minus x squared equals x squared. That is, r squared equals 2x squared. So x equals plus or minus square root r squared over 2, or plus or minus r over square root of 2. Okay, so that's our critical numbers. Plus and minus r over square root of 2. But remember on how this is constructed is, if it's r over square root of 2, that will be, let me put it in a different color. That will be, this will be r over square root of 2. So the negative r over square root of 2 corresponds to over here. But by the symmetry of the problem, that's basically the same thing. So we really only have the one critical number. Okay, so that's we could take something that's like r over 2 versus just r and test this. Now, if you're having trouble conceptualizing how we're testing this, you can plug in an actual value for r. You could do 1, you could do 10, whatever your radius is. But you're just plugging into this formula. And what you're going to get is you're going to get positive, negative, so it's a maximum. Which means our x being r over square root of 2 is what works. Now, you have to go back and say, well, that's our x, which means our width is going to be 2 times r squared root of 2, or 2r over square root of 2. And what's our length? Well, you go back to the fact that, let me clear some space for that. You go back to the fact that y is equal to square root r squared minus x squared, or r squared minus r squared over 2, just by squaring this number, which gives you r squared over 2 again. So r over square root of 2, which since that's the same as what we had with our x, our y is going to be, our length is going to be the same as the width, which is 2r over square root of 2. And that gives you the dimensions of the largest rectangle inscribed in the circle of radius r. So that one's a little bit more complicated and involved problem than some of these other ones that we've done, but I thought it would be good to see an example like that. If you have any questions, comment or message me. But that is what we're going to conclude this section on, and we'll be moving on to antiderivatives tomorrow.